we have no problem with the connection.
Yes, we can hear you. Good morning.
Okay, good morning. Thank you very much for the answer. Can we start? Or we are waiting a few minutes? There are 17 participants. Let's start. Okay, so today I'd like to start the subject about electronic foundation of how the devices of some measurements are built. Today I'm going to discuss about pressure and flow meters, and I'd like to show you what are the principles of this operation and what are different conditions, what are different ways to measure some principle, some physics. Okay, so let's start with the So, as I said, today we are going to tell about the devices for pressure and the flow measurements. Maybe we will have time. I will tell you about something about the position measurement also, but I would like to start with this pressure and flow meters. Okay, so what is the pressure? What are the pressure? We know we are on the Earth. We have the air surrounding us. So more or less 200 years ago, Galileo found that there is something like pressure. I will show you later a film, so you discuss what are the principles of the pressure operation. But at the beginning, we have to say something about what are the different ways to measure the pressure. So first of all, we can define something like absolute pressure measurement. So we do realize that there is something like zero pressure at zero temperature. So this is a vacuum. Okay, this is the absolute vacuum. Of course, this is just a theory because in practice we do not have construct any vacuum, especially on the Earth. Maybe in the space it's easier, but also it's not so easy. So absolute pressure measurements are this measurement of the air, oil, water, or something else pressure that perform so perfect. As I said, perfect vacuum condition I know possible to achieve, but we measure the pressure up to the absolute pressure. So this is the absolute pressure measurements. So this is all of this pressure that are above the absolute vacuum. Okay, so the sensor based on the absolute pressure require strict specification for pressure outputs, because as I said, we have no ideal absolute pressure, so ideal vacuum pressure. So we have to know what is the pressure as set as this vacuum pressure. Okay, so sensor based on this type of measurement I use in the especially in the barometric pressure or in altitude related pressure measurements. So in our planes, in our I don't know, in our cellular phones, sometimes we can find a barometric pressure, or that can be moved into the altitude measurement. So we should know how they work. Okay, the second part of pressure measurements are the differential pressure measurements. As from the name of differential pressure measurements, it means that we have two different pressure and we are going to measure the difference between those pressures, especially if you are if you are making pressure measurements in our environment, in the condition of the at the Earth. So we've got 1 atmosphere of pressure. So if we would like to measure some small changes of pressure, so it is not possible to measure to absolute pressure and subtract them, but it's better to use some differential pressure measurement. It will be explained later how it works. The substitute of differential pressure, the substitute of differential pressure measurement is the gauge pressure measurement. The gauge pressure measurement is in fact a differential pressure measurement, but the one of this pressure is connected with our atmosphere pressure. So this is the differential pressure, but one of these pressures is the atmospheric pressure. Okay, so in the matter of fact, we've got such a situation. We've got, of course, the absolute vacuum pressure, absolute zero pressure, which in the fact we can't obtain, but we can say that we've got some pressure, so we can measure what is the pressure. So we can measure some barometric pressure. This is the pressure between zero pressure and atmospheric pressure, or we can measure some absolute pressures, or we have the pressures above the atmospheric pressure, or we measure the pressure between the atmospheric pressure. So this is the barometric pressure, yes, and absolute pressure. Of course, the barometric pressure is a kind of absolute pressure, but for the atmospheric pressure. So yes, and we've got this second one. So it is a differential pressure. So we can measure any difference of this pressure in this area. And we've got this gauge pressure, or for positive pressure, this is in this case, we can measure the difference between atmospheric pressure and the pressure above the atmospheric pressure, or the gauge vacuum pressure. So we can measure the pressure below atmospheric. Okay, so how it works, I will show you a film.
The most diverse substances are transported and distributed in piping, which can register the tiniest pressure differences in the flowing.
Sorry, it is not this film. We start with this one.
The most varied media are filled into and drained via pipes from tanks every day. Examples are potable water, fruit juices, oils and fuels, acids or brines. Since these media can have completely different properties, there are different measuring principles to detect them. For example, pressure measurement by absolute or gauge pressure, hydrostatic pressure, as well as differential pressure. The first scientific origins of pressure measurement were documented in the middle of the 17th century. Galileo Galilei made tests with pumps to overcome the differences in altitude for irrigation purposes. Evangelista Torricelli conducted research with mercury columns and discovered the state of the vacuum. Blaise Pascal heard of these experiments, continued the research, and could determine the weight of air. Pascal called this force pressure, and to pay homage to him, the SI unit for pressure was named after him. Pressure is the result of a force acting on an area. Pressure instruments may be used to detect absolute and gauge pressures and to determine pressure variables and levels in tanks. First of all, let's have a closer look at the mode of operation of this measuring method using the example of absolute and gauge pressure. Pressures can be measured continually in a pipe flooded with a liquid. We will have a closer look at the difference of an absolute pressure cell and a gauge pressure cell using the example of a ceramic cell. In a ceramic cell, an electrically conductive material is applied to a ceramic substrate, thus forming a capacitor. As pressure is applied, the diaphragm deforms and causes a change in capacitance. The absolute pressure cell is a closed system and measures against the vacuum. In an atmospheric environment, the air pressure is indicated. In a gauge pressure cell, an opening in the substrate permits the pressure compensation between the atmospheric environment and the inside of the cell. The cell measures values which are relative to the ambient pressure. In an atmospheric environment, the air pressure is not indicated. In hydrostatic pressure measurement, the liquid in the tank acts on the process diaphragm of the sensor. Gravity causes the pressure to increase as the liquid column, that is the filling level of the tank, rises. The liquid column is proportional to the filling level and the density of the medium. In an open tank, pressure is continually compensated in relation to ambient air. Therefore, the gas in the upper area of the tank does not affect level measurement. However, in addition to the pressure of the liquid column, the atmospheric pressure also acts on the sensor. In atmospheric pressure compensation, the sensor is called a gauge pressure sensor. Let's have a closer look at such a sensor. The Contype measuring cell is based on silicon technology and has been particularly developed for hydrostatic level measurement. Resistances are applied to a silicon chip in form of a Whetstone bridge. As pressure is applied, the process diaphragm is deformed and a change in resistance results. In the sensor, incompressible oil transmits the pressure from the process diaphragm to a silicon chip where it is analyzed. In differential pressure measurement in a closed tank, the atmospheric pressure is of no consequence for level measurement. Apart from the pressure of the liquid column, the pressure head above the level is also measured. Both values are transferred to the transmitter via oil-filled capillary lines. The transmitter calculates the difference between both pressures and determines the level in the tank from this value. The pressure instruments of Endress and Hauser facilitate the measurement of pressures and levels in standard applications, as well as applications with high temperatures and high pressures, as well as those involving corrosive and abrasive media. We have an appropriate solution for any application.
Okay, this was the example how the differential and absolute, maybe not the absolute, but the differential and gauge pressure works. So, in the matter of fact, can you hear me?
Yes, we can.
Okay, thank you. As you saw, it is possible to measure the hydrostatic pressure using two methods, or the gauge measurement or the differential measurement. So the main principle of pressure measurements is the measurement of the difference of the membrane change. So if you saw it is a membrane there. Yes, this is a membrane in the sensor, and this membrane changed its properties, its shape, is the pressure appears. So we've got the differential pressure, so we've got the membrane and two pressure, one pressure on the one side of the membrane and the second one on the second part of the membrane, or we've got the absolute pressure when one part of the membrane is the vacuum or semi-vacuum, and we measure just atmospheric pressure or absolute pressure, or we've got this gauge measurement when we've got one membrane is connected to the atmospheric pressure, and we measure just the pressure, which is difference between the atmospheric pressure and the pressure we are measuring. So generally, the problem of the pressure measurements is the problem of the measurement of the movement of this diaphragm, or the change the shape of this diaphragm. We've got several construction. I would like you to show you a film which shows you the most common solution.
There are two chips in this housing, a circuit for signal processing and the sensor itself. The micromechanical sensor chip is furnished with a pressure-sensitive membrane. Electrical resistors on the membrane are connected together to form a Wheatstone bridge. Changes in pressure cause the membrane to change shape. An electrical voltage proportionate to the amount of distortion is created at the resistors. The change in voltage is the result of the ambient pressure. In analog sensors, the typical signal voltage generated is between 0 and 5 volts.
Okay, so you can see that was the example of the strain gauge type measurement of the diaphragm, moving the diaphragm and changing its shape. So I don't know, it is the most commonly used situations. So we've got 4 resistors, 4 strain gauge on the diaphragm, and the movement of the diaphragm changes its properties, and then we can measure the difference of the resistivity, and if we supply it in the correct form, we will achieve the difference of the voltage from the Wheatstone bridge. Okay, but we also have a capacitive pressure sensor, so we are we can measure the distance between the diaphragm and the solid state in a capacitive way. So in this case, we've got 2 metal plates and the dielectric sandwich as a capacitors, and the movement of the diaphragm will change the distance between 2 plates, and in this way we will change the capacitive properties of the sensor. Okay, so this is the second one, and we can use, for example, a piezoelectric pressure sensor. So we can use piezoelectric crystals, develop a potential difference. So we do know that piezoelectric crystal changes voltage when we move them, or we change their shape. So in this way we can use the diaphragm by a piezoelectric crystal, and in this way we will have exact voltage changes to the changes of the diaphragm, and this is connected with the measurement of pressure, on differential pressure, on absolute pressure, never mind. So we can use this type of measurement situation. But of course, I hope you in future will discover something more sufficient, more frequent, more stable, and more something better than this situation. Okay, so generally nowadays we've got some pressure sensor. I will show some examples of this, I hope. Okay. Can you see the Farner catalog?
Yes, we can.
Okay, so generally we can divide the pressure sensor into 2 ways. One is the pressure switches, it means that we have set pressure, and above this we switch or unswitch something, and we've got some pressure transducers when we want to measure this difference or different properties of the pressures. Okay, so let's see the pressure switches. They are built in the, of course, there are different construction of this pressure measurement. So you can see it's a lot of possibility to choose. What can we found in this situation? Of course, maybe the most important is the operating pressure. As you can find here, we can find all the switches which can we switch below the atmospheric pressure. Sorry. So we can sense the pressures below the atmospheric pressure and above. I would like to notice that we have no pressure below 1 bar. So we have no pressure below 1 atmosphere, because sometimes some students can say that we've got pipes, for example, that we can use the pressure minus and plus 5 bars, for example. So you remember that we have no pressure below 1 atmosphere because it is below absolute 0. So we rather measure some pressures above the atmospheric pressure. So we can, as you can find out, that we can measure some very small pressure like millibars and some high pressure like a lot of bars. So also you can find here that maybe here it's not so short. Okay, I will show you in the next example. Oh yes, because if you can see, we've got the value of the pressure can be also both in the sea or in the water high or in millibars on the mercury high. So we should recalculate them in the position in the name of the value of the pressure we want. Okay, so first of all we must recalculate psi, for example, for the bars or bar to the psi. Because if we measure something, we must know what we are measuring. Okay, so these are the switches. So some of them are the switches which are just set for a set pressure, but this is the example of switch that we can set the pressure by ourselves. So this is a range of the pressures we can set, and then the output value, so on or off. Because it's usually just two values. Then we can reach the value of the set pressure that we've got on or off. Okay, so these are the examples of the switch pressure, and we've got the second part is the pressure transducer. So maybe for us is more important. So these are the pressure transducers when we can, in the matter of fact, measure the pressure. Because in the switches we just have to switch, just to set a proper pressure, and when the transducer switches just when to reach the pressure. And in this situation, we've got some transducers, and we can measure the output value of the pressure. But we can find out that, for example, here we've got different pressure operatings. Yes, so of course, very small pressures, but this is minus, so this is more or less vacuum, absolute vacuum. But in this case, for example, we can measure very small pressure. This is 1 inch of the water. So you must know that we have to choose a proper transducer for a proper pressure, because we got a lot of difference. Yes, we can very high pressures or very low pressures. Yes, so different type of pressure meters, and we also have to choose the output, because also in this part we have some switches, which are some transducers that are some switches. So we've got NPN or PNP transistor as an output, but it is maybe not important. So we can find. It's not what I wanted to show. Okay, so we've got an analog output or digital. Digital can be different. This is I to C digital, or we can have a current as an output or current voltage. Still digital. We can SPI as a digital. So we have to choose what kind of output we want. So if we use a microprocessor or we use just analog circuit, so we have to choose. Yes, the pressure operating. We have to choose sensor output. Of course, we can choose the pressure type, the pressure measurement type, because we've got, as you can see, differential or gauge or absolute measurement sensor. What's more important? Maybe it's not much important. So, of course, you can see that there are different types of this measurement units. So maybe I will show you some. Okay, maybe I would like to show you some documentation about, I don't know, let's say Honeywell. One of them. Okay, let's see this data sheet. Okay, so you can see that it's a lot of physics. Okay. Of the shape of this sensor. We've got one housing sensor, so it is an absolute sensor or gauge sensor, and a differential sensor. Of course, this is just the example. What can we see here? We've got some characteristic of each of the sensors, so we know that is 6 volt as an absolute output, but maybe okay, so this is the better. Okay, so we've got a documentation of the sensor. As you can see, it is usually it's a voltage supply. This is the current. What this sensor needs, and operation temperatures, compensated temperature. So we must find out if it compensated or no. Here we can see that is compensated up to 50 Celsius degree. Temperature output option. In this situation, we've got some in this digital solution. We've got some compensated. You can temperature output, so to compensate the pressure measurement, and so on and so on. So if you will use, I hope you will use such a device, you have to choose what you want. In the matter of fact, so we can. That was the example of such a construction. Here is another construction. So in the matter of fact, it's a lot of solution, and you will have to choose. Okay, this is the series, and you can see that in this 24PC series, we've got different pressure ranges, different materials, different pressure type, ports, the hosing, and different temperatures. So this is the one of the principle, and you have to choose, of course, what you want to measure, because if you want to measure water, there are different pressure measurement devices, because it needs a diaphragm with metal. And if we measure a pressure of the air, we do not need a metal, so it can be a silicon or something like this. Okay, so, or if you are going to measure some aggressive substances, you need a stainless steel diaphragm. So there is a lot of solution, a lot of properties you must know. Okay, so in the matter of fact, as I said, there are a lot of elements you have to pay attention. So the main important, of course, is the measuring range or the measuring method as the beginning. So you must find out what are the minimum and the maximum pressure you want to measure, because we have to choose a proper device. Of course, we have to know what are the operating temperature, because there are different solutions for the low temperatures, for high temperatures, different solution for the space, different solution for the inside air measurements. So there are different pressures, different temperatures. Of course, the dimension sometimes play a big role, because we want to be something to be smaller and smaller. So if we are using some pressure measurements, for example, for altitude in the cellular forms or in our devices which are measure the altitude, so it should be small. Of course, the accuracy, reparability are the typical elements of the specification, which are typical for the sensor, for all type of sensor, not only the pressure type of sensor, and the output type. It is necessary to find out if you want to digital, analog, or compensated, or just a Winston bridge, or it is some amplifiers there, so a different solution to choose. Okay, the response time is also important, because if you are going to measure some fast changes of the pressure, for example, for acoustic elements, for acoustic pressure measurements, so we have to choose a device with the fast response time. Okay, so as we can find out, there are a lot of solutions, a lot of properties of the pressure measurements devices. Okay, any questions about this subject? Can anybody hear me?
No questions yet, I guess.
Okay, thank you very much. Okay, so now I would like to move to the next subject. It is the subject connected with the flow, liquid flow measurements, for example. In this subject, maybe it's not important to remember what are the differences of the flow measurements, but I would like you to show how many physical properties can be used to measure, for example, the flow meters. I will show you some films, because the flow of the water, the flow of the gases, the flow of the oil are very important in our environment, in our measurements. So I will show some films to show you how many different solutions are able to measure the flows. Okay, let's start with the differential pressure. This is the base measurement.
The fluids flowing through pipes often have completely different properties. Therefore, different principles for their measurement are required. One method is flow measurement, based on the differential pressure principle. Some 300 years ago, Swiss mathematician and physicist Daniel Bernoulli discovered the direct relationship between the pressure and speed of a fluid flowing in a pipe. Italian physicist Giovanni Battista Venturi also performed experiments on flow, and in 1797, he built the first flow meter for closed pipes, known as the Venturi tube. Here is how this measurement method works. Differential pressure flow meters have an artificial restriction integrated into the measuring tube, illustrated here by the example of an orifice plate. Two holes are located in the pipe wall, one before and one after the orifice plate. Two separate tubes connect these holes to a differential pressure sensor with its two pressure chambers separated by a diaphragm. The tiniest pressure differences in the flowing fluid can be precisely measured. If the fluid is not flowing, the pressure before and after the orifice plate is essentially identical. As soon as the fluid starts to flow, its velocity around the orifice plate increases significantly because of the restriction in the cross-section. At the same time, due to the laws of fluid mechanics, the static pressure at this point decreases. Consequently, different values are detected in the pressure chambers of the sensor, a higher pressure before and a lower pressure after the orifice plate. This pressure difference is a direct measure for the flow velocity, and thus the mass and volume flow in the pipe. The higher the flow velocity and the resulting drop in pressure around the orifice plate, the greater the differential pressure measured. In numerous industrial applications, the orifice plate covers many needs of flow measurement technology. However, other designs are available for certain measuring tasks to minimize undesired effects, such as excessive pressure loss or abrasion of components due to solids carried in the fluid. This demonstration shows that an abrupt restriction generates severe turbulence in a fluid. Nozzles with a rounded, funnel-like inlet clearly reduce turbulence and thus create less pressure loss. Nozzles are particularly suitable to higher flow velocities or to fluids with abrasive solid particles. Turbulence reduction is even greater with Venturi nozzles. And finally, with Venturi tubes, where the restriction is created by longer conical constrictions in the pipe wall. All these designs can be supplied with different restriction diameter sizes, so that the pressure loss and the differential pressure generated can be optimized for the process conditions.
Okay, so that was the example of kind of the flow measurement basics on the differential pressure measurement. So in this way, we've got first it was a plate, and it was shown that if we have some fluid or some air going through this plate, we have a higher pressure at the beginning and the lower pressure at the end of the plate. But as it was on the film, this kind of plate caused that we've got the high reduction of the pressure. So we've got the bigger pressure loss in this pipe. So it's better to use, instead of oriflace, we could use some flow nozzles. In this situation, in the same situation, we measure the differential pressure between the input, before the nozzle and after the nozzle, and this obtain the difference of the pressure is connected with the flow of the gas, both the volume or the mass flow of the gas or of the liquid. And finally, the Venturi tube discovers some shape of this tube that causes small differences of the pressure in this situation, small losses of the pressure, so losses of the flow. And we can, the same situation, we can measure the difference of the pressure and measure exactly the flow. But if you can see on this chart, there are different properties of this solution. For the oil phase, we've got a linear solution, the connection between the flow and the differential pressure. For nozzle, we've got some logarithmic one, and Venturi, as we can see, it's much smaller, so there are small losses in the pipe, but maybe it's not a problem for us to linearize such a curve. Okay, so that were the examples how we can measure the flow velocity, how using the differential pressure, but we can have different solutions. And next film.
Carbons and The fluids flowing through pipes often have completely different properties. Therefore, different principles are required for their measurement. One principle is flow measurement based on dynamic pressure detection using a pitot tube. Some 300 years ago, Swiss mathematician and physicist Daniel Bernoulli discovers a direct relationship between the pressure and speed of a fluid flowing in a pipe. At the same time, the French engineer Henri de Pitot is constructing a device for measuring the traveling speed of ships using flow pressure. His instrument is known as the pitot tube. Here is how this measurement method works. Pitot tubes have a rod-shaped measuring element that is inserted into the pipeline perpendicular to the flow direction. On the front and rear of this probe are several holes. Two separate tubes connect these holes to a differential pressure sensor. With its two pressure chambers, separated by a diaphragm, the tiniest pressure differences in the flowing fluid can be precisely measured. The individual pressure taps are distributed along the entire pipe cross-section to ensure a representative measurement. If there is strong interference in the flow profiles, it's advisable to fit a second pitot tube, rotated by 90 degrees. If the fluid is not flowing, the pressure before and after the probe is essentially the same. As soon as the fluid starts to flow, an additional impact pressure against the front of the probe is generated, also known as the dynamic pressure. On the rear of the probe, in contrast, only the static pressure, which is not related to the flow, is still measured. As a result, different values are detected in the pressure chambers of the sensor. Higher pressure against the flow and constant pressure on the rear of the pitot tube. This pressure difference is a direct measure for the flow velocity and thus the mass and volume flow in the pipe. The higher the flow velocity and therefore the dynamic pressure, the greater the differential pressure measured. Pitot tubes are able to register the flow in both flow directions. This means that balancing measurements, for example in gas pipeline networks, can be carried out at any time. Continuous improvements have been made to pitot tubes over the past decades. Devices with a built-in temperature sensor, for example, together with a flow computer, can also calculate temperature-dependent mass and energy flows.
Okay. So that was the example of the pitot tube. So in this situation, you can find out that there are some elements that are connected with the dynamic pressure, connected with the flow of the elements, flow of the or water or oil or gases. So it was firstly discovered for the ship movement, for the ship velocity, how fast it moves. This type of measurement has the advantages that we do not need a tube in a matter of fact. It can be open area, open space, or water or air. So the pitot tubes are used in the ships, as we said, but also in the airplanes to measure the velocity of the outside air, or in the same the velocity of the plane in fact. So they are very useful for such a measurement. So that was the second solution, how we can measure the flow. And the next one.
The basic physics of this principle can be flow measurement based on the electromagnetic principle. The basic physics of this principle can be traced back to the English physicist Michael Faraday, who in 1831 discovered that electrical current can be generated with a magnetic field. Roughly 100 years later, the Swiss inventor and priest Father Bonaventura Turliman applied this knowledge to electrically conductive liquids flowing in pipes and built the world's first electromagnetic flow meter. Let's take a closer look at how this measurement method works. Two field coils are located inside each electromagnetic flow meter. With the help of what are termed pole shoes, these coils generate a constant magnetic field over the entire cross-section of the measuring tube. Two electrodes which can pick up electrical voltages are installed at a right angle in the wall of the tube. The lining fitted on the inside wall prevents electrical short circuits between the conductive liquid and the metallic tube. If there is no liquid flow, no induced electrical voltage is measured at first between the two electrodes. The electrically charged particles of the conductive liquid are evenly distributed, shown here in water with red and blue particles. However, as soon as the liquid starts to flow in the measuring tube, the magnetic field applies a force to the charged particles. As a result, the positively and negatively charged particles in the liquid are separated and collect on the opposite sides of the tube wall. Now an electrical voltage forms, which is detected and measured by the two electrodes. This voltage is directly proportional to the flow velocity in the pipeline. Together with the known tube cross-section, the flow volume can then be calculated. The greater the flow velocity, and thus the separation of the charged particles, the greater the electrical voltage between the electrodes. The electrodes also detect what is called interference voltage, which has to be separated from the actual measuring signal. One method that has been successfully used for this purpose is to create the magnetic field with a pulsed direct current. To do so, the polarity of the magnetic field is alternately reversed, illustrated here in slow motion. The voltage picked up on the measuring electrodes now constantly changes in polarity. As a result, all constant interference voltages can be eliminated. For example, electrochemical effects in the liquid, or external electromagnetic fields. Thus, the size of such interference voltages has no impact whatsoever on the actual measuring signal. The advantages of this are a stable measurement and a stable system zero point. With an installed base of over 1 million electromagnetic...
Okay, so you can see that we can have a construction. The advantages of this construction is that there is no barrier inside, so we have no pressure loss. But this can be used only for liquids, for water, as a matter of fact, which have two different polarity. Okay, so this can't be used for oil or gases. Is the matter of fact. Okay, but we can discover some. Okay, now this is another type of measurement.
Have consequently different principles for their measurement are required. One method is flow measurement based on the vortex principle. In 16th century Italy, Leonardo da Vinci observed how vortices form in flowing water. Some 400 years later, Hungarian physicist Theodor von Karman described the physical laws that govern how these vortices take shape. Here's how this measurement method works. Inside each vortex flow meter, a bluff body is located in the middle of the pipe. This body is a kind of obstruction that disturbs the flow. Downstream from the bluff body is a mechanical sensor which can register the tiniest pressure differences in the flowing fluid. If the fluid is not flowing, no vortices form. As soon as the fluid starts to move and reaches a certain flow rate, vortices gradually appear downstream of the bluff body. These vortices are detached alternately on either side of the bluff body and are carried away by the flowing fluid. Zones of high or low pressure now appear downstream and thus create a phenomenon that is known as the Karman vortex street. These differences in pressure exactly match the frequency of the passing vortices and are precisely registered by the mechanical sensor, shown here in slow motion. This sensor is unique because it's inherently so well balanced that pipe-borne vibrations of up to 1 G, pressure surges, and temperature shocks have no effect whatsoever on the measurement. The distance between two consecutive vortices corresponds to a defined volume of fluid. Therefore, total flow can be calculated by counting the vortices that pass. The higher the flow velocity, the higher the measured frequency of vortices. In some applications, the velocity is too low for perceptible vortices to form. However, the velocity can be increased simply by installing a vortex meter that has a reduced cross-section. This modification does not affect the measuring accuracy. Functionality can be enhanced by incorporating optional temperature measurement into the sensor. A configuration like this, together with a built-in flow computer, can calculate temperature-dependent mass or energy flow.
Okay, so another physical properties we can measure. This is the connected with the flow. So that was the vertex flow meter. Of course, we can another solution is the temperature meters.
Flow measurement based on the thermal principle. The basic physics of this principle can be traced back to the Canadian physicist Louis Vaisseau-King. In 1914, he mathematically described heat transport in flows. Here is how this measurement method works. Inside thermal flow meters are two temperature sensors protruding into the measuring tube. They're known as PT100 resistance thermometers. One of these temperature sensors measures the actual gas temperature as a reference, regardless of the flow velocity. The second temperature sensor is heated constantly via electrical energy, so that a predefined temperature difference is maintained between the two sensors. For example, 10 degrees. If there is no flow, the differential temperature between the two sensors does not change. As soon as the fluid begins to flow in the measuring tube, heat is drawn from the heated temperature sensor via the gas flowing past. The heat then is carried off by the flow. The corresponding cooling effect is measured and compensated immediately by adding more heating current. As a result, the target temperature difference is continuously maintained. The heating current required to maintain the temperature difference is proportional to the cooling effect, and therefore is a direct measure for the mass flow in the pipe. The greater the flow velocity, and therefore the additional cooling of the heater sensor, the greater the heating current required. An alternative adaptation of the principle keeps the heater current at a constant value, and then measures the change in temperature differential. But how is the heat actually transferred from the heated temperature sensor to the gas flowing past? This sequence shows that the heat is transferred by the gas molecules themselves. When the gas flows past, the molecules absorb tiny heat packets and carry them along with the flow. The faster the gas flows, the more often they absorb the heat. The heat transfer also depends on the density of the gas because at a higher pressure or lower temperature, there are more gas molecules in the pipeline. The greater number of molecules results in more contact with the heated sensor, meaning increased cooling and thus increased heating current flow. And finally, the heat transfer is also affected by the thermal properties of the gas. For example, at the same mass flow, the high thermal conductivity of hydrogen, shown here in green, causes cooling that is 100 times greater than with air. For a precise measurement, it's therefore important that the specific properties of the gas are known and are consistent. Flow measurement using the thermal principle is also possible in large pipes and ducts. There are meter types designed specially for this application. They can be inserted directly into the pipe via a standard process connection. It is important that the required insertion depth be respected so that the measurement is carried out at the correct point. For that reason, it's essential to program the actual internal pipe diameter for all insertion meters. Correct insertion also applies for rectangular and square ducting, often found in factory or building air circulation systems. With thermal mass flow meters from Endress.
Okay, so as you can see, we can use a term differential pressure measurement. We can, for measurement of the flow, we can use some mechanical properties of the gas. We can use thermal properties of the gas, but engineer didn't stop. And for example, we've got ultrasound principle of the flow meter.
The physics of this principle can be traced back to the English physicist and Nobel Prize winner Lord Rayleigh. His book on the theory of sound, published in 1877, describes the propagation of sound waves in solids and gases. Here is how this measurement method works. Inside the ultrasonic flow meter, pairs of sensors are fitted across from each other in the measuring tube. Each sensor can alternately transmit and receive an ultrasonic signal. Simultaneously, the transit times of these signals are measured. The ultrasonic signals are generated with piezoelectric crystals applying a voltage. Conversely, a piezoelectric crystal creates a voltage when an ultrasonic signal impacts the sensor. By increasing the number of sensor pairs, it's possible to accurately detect and mathematically compensate for flow profile distortions over the entire pipe cross-section. When there is no flow, the signal transit times are the same, upstream and downstream. Once the fluid starts to flow in the measuring tube, the ultrasonic signals are accelerated in the direction of the flow and decelerated against the flow. As a result, the ultrasonic signals now have different transit times, less time in the direction of flow and more time against the flow. Therefore, the differential transit time measured by the sensors is directly proportional to the flow velocity in the pipe. Together with the known tube cross-section, the actual flow volume can then be calculated. The greater the flow velocity, the greater the measured time difference between the two ultrasonic signals. For ultrasonic flow measurement, the sensors do not necessarily have to be fitted into the pipe wall. With a clamp-on system, for example, the sensors are fastened directly onto the outside of the pipe. They can be retrofitted at any time without interrupting the process. With clamp-on sensors, the ultrasonic signal is passed directly through the pipe wall and into the fluid. The signal continues through the fluid, is reflected on the opposite pipe wall, and then measured by the second sensor. In this example, with a 2-traverse installation. The clamp-on design is unique because flow rates can be measured in very large pipes, up to 4 meters in diameter. This possibility increases the areas of application, for example in the water and hydroelectric industries. Flexible mounting, process safety, and cost effectiveness are the distinctive advantages of ultrasonic flow measurement.
Okay, so that was the solution, how we can measure flow using ultrasound signals. Okay, I will show you this one.
Point level measurement. There are different measuring principles to detect them. For example, point level measurement in liquids or bulk solids according to the vibronic principle, called also tuning fork principle. The tuning fork, which John Shore designed more than 300 years ago, served as a basis for the vibronic principle invented by Endresen Hauser in 1967. This principle uses the direct correlation between oscillation and damping in media. Let's have a closer look at how this measuring method works. Vibronic instruments monitor point levels in tanks, containers, and pipes. A sensor, in form of a tuning fork, is excited to its resonance frequency. The vibronic measuring principle in liquids is based on the resonance shift of a piezoelectrically excited oscillation system. There are 2 different piezoelectric drives, the bimorph drive in standard instruments and the stack drive in coated instruments. The bimorph drive consists of 2 discs, a piezo and a ceramic disc, which are connected to each other. At the same voltage, the piezos are compressed and the ceramic disc is bent. At different voltages, the piezos expand again. This causes the oscillations of the fork. The stack drive, however, stacks and fixes several piezo discs with changing polarization on top of each other. The application of a respective alternating voltage also causes the piezos to oscillate. As the piezos expand, the membrane is bent to the outside. The ends of the tuning fork, which is attached to the membrane, are pushed apart. As the piezo contracts again, the membrane is bent to the inside. The ends of the tuning forks, attached to it, are pulled together. As the tines of the fork are covered in a tank as the liquid rises, the resonance frequency of the tuning fork changes. The immersion into the liquid reduces the frequency. This frequency change is It's analyzed and converted into a switching signal. In solids measurement, only the piezoelectric stack drive is used. As the bulk solids cover the fork, the oscillation is damped. This changes the amplitude of the oscillation. The change is analyzed and converted into a switching signal. The vibronic measuring principle of Anderson-House.
Okay, maybe it was not a good example of a flow measurement, but it also shows how can we measure differences, different properties of the substances. And the last, maybe not the least, but I will show you the last example of the flow measurement. This is the, I would like you to pay attention about this type of measurement because it is based on the Coriolis effect. I hope you heard about the Coriolis effect. This is important because this type of measurement can measure both the mass flow or they can measure volume flow or can measure the properties of the substances. So in one Coriolis effect, we can measure different properties of the substances that are inside the tube. So it is, let's say it's a gold standard. It's a gold standard for the flow measurement, and it's very important. Maybe not so easy, but as a principle, but it is a gold standard. So I would like you to pay attention how it works.
Measurement according to the capacitance principle. The oldest capacitor design goes back to Ewald Georg von Kleist and Peter. The space between.
Okay, so sorry, it's not this film. It's not this film. Coriolis, this one.
Oil and acid. The fluids flowing through pipelines often display completely different properties. Consequently, there are different principles for their measurement. One such method is flow measurement based on the Coriolis principle. The French physicist Gaspard Gustave de Coriolis set out the physical basis for this measuring principle over 200 years ago. What is interesting is that the Coriolis principle allows the flow of mass to be directly measured. Let's take a closer look at how this measurement method works. A tube is located inside each Coriolis flow meter. An exciter causes this tube to oscillate constantly, here in an exaggerated example. If there is no flow, the measuring tube oscillates uniformly. Sensors are located at the inlet and outlet and register this basic oscillation precisely. As soon as the fluid starts to flow in the measuring tube, however, additional twisting is imposed on the oscillation as a result of the liquid's inertia. Now, due to the Coriolis effect, the inlet and outlet sections of the tube oscillate in different directions at the same time. The highly sensitive sensors pick up this change in the tube oscillation in terms of time and space. This is known as the phase shift and is a direct measure of how much liquid or gas is currently flowing through the pipe. The higher the flow velocity, and thus the total flow, the greater the deflection of the oscillating measuring tube. The application of the Coriolis measuring principle doesn't stop here. It can also be used to simultaneously determine the density of the flowing fluid. To do so, the sensors also register the oscillating frequency. In other words, how often the measuring tube moves back and forth in 1 second. From the animation, it's clear that a tube filled with water oscillates more frequently than a tube filled with honey, for example, which has a far higher density. Thus, the oscillating frequency is a direct measure of the fluid's density. Both the density and the flow are determined simultaneously but independently via the tube oscillation. Endres and Hauser has continuously revolutionized.
Okay, so that was the example of the Coriolis effect principle for operation. So we had this, for summarizing, we had this plate, so with some separation in the tube principle, and the measurement of the differential pressure is the measurement of the flow. So we've got the Oriflate, nozzles, and Venturi tube, which are different solutions. Could find out some flow, especially for air measurement, flow measurement of the air. We can find out some variable area for flow meters that are called rotameter. So it is an element that flies in this moving air. So if there is no flow, it's down. The flow is higher. It's caused that this element goes up. So in this way, we can more or less measure the flow. Or we can have this pitted tube, which is usually used for ships and the planes, because this kind of flow measurements can operate in the open space. It doesn't need any pipe to measure. Or we can use this temperature measurement, so calorimetric measurement. It also can measure the flow both in the pipes or outside. And we found what are the vortex, how they are formed, and how we can measure just by a mechanical elements. So they are very simple, and we can use it everywhere. But in this case, we have some elements which disturb the flow, so they change the properties of the flow, and some pressure differences and energy loss are appeared here. Electromagnetic. So as we could see, it's very easy, but only for substances that have the electromagnetic fields elements. So just for some water elements or something like this. And we can discover what are the ultrasonic Doppler properties of the properties and the principles of the flow measurements. As we could see, we could use them for larger pipes, for the elements. They are very important to measure, not very exact measurement of the flow, but we don't want to integrate into a pipe, for example. So we can install the ultrasonic outside the pipe and measure the flow of the elements inside. We find out what is this Coriolis, and we know that the oscillation frequency is connected with the kind of fluid, kind of gas that inside the density of the gas can be measured by the measurement of the oscillation, the time of the oscillation. And if any flow appears in these elements, the twist angle is connected, maybe not linear, but we can linearize it. It's connected directly to the mass flow that appears in this element. Okay, this is. I think it's all for today, because I'm not going into none of this kind of flow measurement. If you are interested more into one of them, you can find out what are the properties. You can find out the solution from different manufacturers. You can find out what are the pros or why we use them or why we do not use them. So I leave you some time to study it yourself. Okay, so it would be all for today. If you have any questions, I'm open. Do you like this type of lecture? Do you prefer some films, or do you prefer some lectures just then I'm talking?
It's nice to see the principles of the sensors visualized with animations.
Yes, I think so. It's in this case, it will be nicer to see what's going on inside that, just a theory how it works. Okay. Okay, so if there is no questions, thank you very much for today. If anybody has questions, please write me an email or write on the chat. I will be for a few minutes on the chat. Okay, thank you very much.
Thank you. Goodbye.